Uh, Hi everybody, I'm Vishwanath. Currently, I'm a postdoc at Institut de Physique de Nice, University Côte d'Azur, Nice, France. And today I will be talking about turbulence in Fourier truncated Gross-Kaczynski equation and two fluid models, primarily Hall-Wine and Bekarovich-Kladnikov model. I mean, it was advertised that I will be talking about turbulence at finite temperatures, but since Mark Brichet is here next week, so he will be talking mostly about that. So I will just simply touch few things and move on. So the work I will be presenting is mostly collaborative. So Mark will be here next week, Ravi is already here. And most of the work is also Rahul and Akhilesh, who's a student at Indian Institute of Science, Bangalore. So we are concerned with superfluidity, and it occurs in a quite wide variety of substances. For example, liquid helium below 2.17 Kelvin, its fermionic counterpart at subpart millikelvin or atomic BECs, and exotic neutron stars. So what it is a dissipation-less flow past obstacles or through narrow channels. And it is a quantum mechanical behavior on a microscopic scale and invariably linked to BECs, and people have gone through this this week. So, and then to discuss some of these exotic properties of these superfluids, Landau and Tisa propose a so-called two-fluid model in which you have a physically inseparable mixture of two fluids, a normal component and a superfluid component, described by the density rho s and rho n, and each of them have their own velocity field, and so that you can write a mass current density rho s times Vs plus rho n times Vn, which gives you to the total mass current density. And here is the variation of the density fraction as a function of temperature, which was inferred from Andronikashvili experiment long time back, and some of the speakers have already touched upon it. So we are concerned with now with turbulence and what is it. So for our purpose, we will take it as a dynamic field that is spatially complex, aperiodic in time, and involves fluctuations that vary across a wide range of length and time scales. So, I mean, this is what was proposed as a kind of a lucid thing in this review article by Pauletti and Lathrop. And we know from experience with classical fluids that turbulence motion involves rotational motion. And we also know that in superfluids, the rotational motion comes through quantized vortices. And as long back as 1955, Feynman proposed that we can have a sort of a turbulent motion in superfluids. And how? It's like by having a dynamic random interacting tangle of quantized vortices. For example, here is a, let's say, bunch of vortices, line vortices interacting. And you have a complicated shape. So this is not without experimental validation. So there have been some experiments in Bose-Einstein condensates where such a motion has been inferred, from the density visualization of the Bose-Einstein condensates, where the turbulent motion was excited by application of an external oscillatory perturbation in the trap. And for example, here you see a schematic of the vertical distribution. And also, Cambridge group recently did some experiments where they studied. Yeah.
So in this setup, however, you lack the range of landscapes. So
yes. So that's what I was going to say next. Like recently in Cambridge experiments, they did study some direct cascade. And here it just gives you here it just, you don't have a range of scales, but the notion is there that you have a random tangle, but very few vortices. System size is very small. I will come to the length scales later. And in case of classic superfluid helium, one of the earliest, I mean, for the helium-4, one of the experiments which was conducted around 1998, that you take superfluid helium in a container and excite it by means of two counter-rotating propellers. So this generates a turbulent motion, and they recorded the pressure fluctuation from which they inferred the velocity fluctuations and reconstructed the energy spectra and also studied some higher order velocity statistics. And they did this experiments at temperatures above the superfluid transition temperature and below the superfluid transition temperature. And what they found is that the energy spectra is more or less is the same both above and below the transition temperature. And similarly, the higher order statistics of the velocity increments which they computed were also quite similar. So they inferred that the superfluid turbulence in liquid helium is very similar to the classical turbulence. Now, now we will try to make sense of length scales. Carlo already pointed out a limitation in one of the DEC experiment. So in the case of helium experiment, specifically I'm talking about the experiment which I showed just now. So the heating length which gives you the size of the vortex core is of the order of 10 to the power minus 10 meter in helium-4. And the intervortex spacing is something of the order of 10 to the power minus 5. And the system size for the previous experiment is of the order of 10 to the power minus 2. I think it was 20 centimeter there. So if you look at the ratio of the box size of the container size to the vortex core size of the order of 10 to the power 8, it's huge. Okay. And now if you switch to recent BEC experiments, the range of the scale separation is not that large, and the core size is tunable and is of the order of 0.5 microns. And the intervortex separation is something like 10 healing lengths. Okay. And the length scale or the size of the BEC is like maximum to the is maximum of something like 100 microns. So you don't have a very large scale separation here. Okay. So now we come to the popular approaches, theoretical approaches which have been used to study these processes. But I must comment that I mean, since a huge range of length scales are involved, not I mean, no theory covers the entire range of length scales and talks about all the phenomena which are involved in a superfluid turbulent motion. So one of the most popular microscopic approaches is classical Grosseteste equation, which is valid at low temperatures for a weakly interacting those gases. It accounts for the phenomena at the length scale of the vortex core, or you can use a so-called vortex filament model. So there you make distinction between the individual vortices, but you ignore the nature of the vortex core. But this model is valid at length scales which are much greater than the vortex core size. I mean, or any other length scale involved in the problem. I mean, could be I think 1,000 core size. And the third approach, which is a continuum approach, is called Hall-Winen-Bekarovich-Palatnikov model. Is a generalization of the two-fluid model, which includes vortices, but with the difference here that we don't distinguish between the individual vortices. We consider continuum of vorticity, and this relies on the polarization of vortex lines so that you can construct or reconstruct a macroscopic velocity field. Okay. So I will begin with GPE description. So here is a Grosseteste equation Psi is a complex scalar field, and this equation conserves the total energy, total number of particles, and if there's no external force, it also conserves the total momentum of the system. And you can recover hydrodynamical description if you make Medley transformation. You can get density and velocity, which is now given by the gradient of the phase of the wave function. And now you can have vortices here, which are essentially zeros of psi. And this transformation is singular on points in 2D, on lines in 3D, and quantum circulation around these lines is quantized in units of h by m. Moreover, this system supports sound waves. So if you linearize the Gross-Petersky equation around the constant condensate, you obtain a Bogoliubov dispersion relation where which is like k squared plus k to the power 4, with and the speed of sound is given by the ratio of the interaction strength times to the, okay, I should not say that, but it's just given by this expression, and the hearing length is given by this expression, which you can obtain by the balance of the kinetic term and the interaction term. And this also sets the scale of the of the vortex code. And I can use these to simplify and write it like this. And now I have a dispersion relation in terms of the speed of sound and the hearing length. And this and let's say in your system you have maximum the k, you have a maximum k, and so that you have psi k max, okay, and that will set the maximum amount of dispersion in your system. Now to study turbulence in such systems, we will develop some diagnostic tools which were introduced like 20 to 25 years ago. So we split the kinetic energy, total energy into three parts. Kinetic energy, given by this, the internal energy, the quantum pressure energy. Moreover, in turbulence, we are mostly interested in the statistical characterization of the field and how the energy is distributed across various length scales. So we introduce energy spectrum, which is given by this expression. Okay, and furthermore, we can split the kinetic energy into compressible and incompressible part, making use of the Helmholtz theorem, so that the incompressible part is carried by the vortices, and the compressible part is contained in the.
Can I ask a question to you? You see, this is a little bit unlike classical hydrodynamics, because the rotational, irrotational parts are distinguished by the curl and chain. Well, you don't have curl and chain, and you have square root of rho. So you should have rho b, you know, the rotational flow, right? So you see, this is the distinction between the two, and to what extent. Can you discuss to see why? I understand you see that there are formal, but not so much physical reasons to do this. See, so I have difficulties with this problem.
I mean, we do this.
You understand my question, right? You see, classical hydrodynamics, irrotational flow is defined to see like rho v, the divergence of that, not square root of rho. You don't have square root of rho in classical hydrodynamics.
Yes. I mean, here we are essentially doing this to make this velocity field in the presence of, vortex, which has 1 by r behavior, to make it divergence free. Because near a vortex, I mean, this guy goes as r and 1 by r. So, I mean, you are basically trying to smoothen.
I think our question is just why do you have square root rho, and I think that's the process you can do both. This is just simple because squared gives the right expression for the kinetic energy. So I mean that was discussed in this first paper by does it who introduced that? That it's just an arbitrary choice. The only thing
No, I'm saying it's arbitrary.
Yeah, you do it before the alpha violet. Because you need an alpha violet regulator, because otherwise it's not well defined.
So it's simply because of the unpleasant mathematical problems.
Yes.
There is some physics too. If it gives some singularity, it's not something you can put on the right.
No, there are two things. The goal is just to have an energy spectrum of the kinetic part. The kinetic part is raw gas body. This is a part. Then you want to have energy spectrum, so the energy partition.
That one, you see, doesn't contain square root of rho because you square. It's rho v squared.
Yes, this is the kinetic.
Yes,
Yeah. Then you want to compute the spectrum of that. So you could, for instance, have taken the cross spectrum of the Fourier transform of rho times the Fourier transform of v squared.
I'm sorry.
That's a choice. No? Now, what is the energy spectrum?
But if I'll do this in classical hydrodynamics, I wouldn't do this way. This is what I'm saying.
Actually,
nobody does it. See, I take lamp. You don't find
people in compressible fluids, there is no a unique definition of the kinetic energy spectrum because it's composed of three.
Well, they define rotational spectrum, the rotational flow, you see pretty clearly in classical hydrodynamics. That's what I'm saying.
For compressible fluids?
For compressible fluid. Even a compressible fluid.
No, for incompressible, it's very clear.
Right.
Yes.
Makes no difference.
Yeah.
So what you want is just to have an expression such that you make the integral of k and you get the total kinetic energy. So you can do it in several ways. At the end, it's rho v squared. You can take rho times v, square root of rho v times square root of rho of v, or an arbitrary power. This, I accept that it's arbitrary. Why do you put it this? Because it's the same, it's a square, so it has a meaning, it's quite similar.
No, the sum is the same, you see, but the separation is not.
It's arbitrary. But the good thing of this, that you put the good power such that everything is regularly controlled. Yes. And this is as a physical argument. Because at the end of the day, this is just the gradient of size, what is a regular thing on the vortex point.
I mean, the problem is just coming from the transformation.
Yeah.
And it's just that you have this term here and you can define it as a field. And so, you know.
The divergence of the compressible part.
No, you see,
is that
it's still, I don't completely agree. So if I take the vortex in quantum mechanics, I look at the quantization of the phase. It doesn't contain rho at all.
Sure.
Yeah. But here you do.
But the kinetic energy has rho.
Yes.
Yeah, but you don't have gradient of rho. This is what I'm saying. You see, when you calculate the energy of the vortex, you see, you have gradient of the phase. You have the gradient of the phase. You see, if I calculate in two different ways, you see the energy of the vortex, I take two different relations. They don't contain the same energy.
Yeah,
you calculate
the
this way.
The energy of a vortex, you have to add up everything. You have to add the kinetic and what's called the quantum energy that it contains.
If I calculate, you see, using the upper formula, you see the first one. In the case of a vortex, it's simply density and the velocity.
Yes.
And the velocity is the gradient of the phase alone. But if I do it this way, you see, I have two terms which then don't appear. So okay, maybe you should leave it.
Come back. Discuss this afternoon.
So this one is, okay. So
let's leave it.
We'll bring it up. Okay, won't be here. At the end.
Just one quick question. The vortex core structure, R dependence for classical fluids is proportional to R square or proportional to R? Okay.
Classical fluid, you can tell what the symptoms are.
Yeah, you don't need a core.
So the peculiar feature of this problem is that it's impossible to keep the density constant in a particular fluid. Once you get vortices,
no, but you have the same problem in classical dynamics. They're not wholly incompressible, right? You look at gases, you look at the dynamic fluid of the gases, they're compressible. But I think you can define what it's a tornado day, right?
You can study turbulence with essentially vortices constant density. This is not the case here.
What do you think they define the vortex in case of tornadoes? You can see this in the air. You see, that's compressible, and I don't think they have square root of rho in that case. to classical dynamics. You see, I think this is a pure thing which appears in this particular treatment. You see, so I don't think you'll have that in climate. You see, if you open any papers, they don't get square root of rho.
We'll come back.
Okay, so so here I will be working with Fourier truncated GPE and truncation in Fourier space for any numerical computation of GPE partial differential equation can be written like this, where f is a nonlinear function which contains psi and its powers, let's say. Of course, in Fourier space, and it will contain convolutions here. So, and what I impose by saying that I'm truncating Fourier space is that I define a k max and I put all the modes above that to 0. So essentially, I'm working with n c squared, let's say, number of collocation points, and my PD. This description is approximate, the truncated system approximates the PD only as long as the spectral convergence is ensured, and we will see examples of this later. So what we have essentially is a finite dimensional system of ordinary differential equations because of this truncation, and this will display, this will have standard statistical mechanical properties including that. For example, in the case of those gases, it has been shown truncated Gauss-Piquet's equation at its microcanonical ensemble, or one can generalize it to have a grand canonical ensemble. So, and this also serves as a simple model for finite temperature to include finite temperature effects in those gases. For example, you impose what I just said before, you impose an ultraviolet cutoff on the GPE, and you restrict it to some K max, which depends on your, let's say, numerical scheme. And then you basically obtain a truncated Gauss-Piquet equation. And it has been shown that a long time integration of this equation for some generic initial conditions generates microcanonical equilibrium states. For example, Matthew Davis, like long time back, had studied this for a 3D homogeneous Bose gas. And sometime back, Mark and Giorgio did this computation again, but they also at the same time generalize it to grand canonical probability true states, where you can introduce a probability distribution function given by this expression, and you can construct a Langevin equation. You can construct a stochastic process which obeys a Langevin equation, which is simply the stochastic Ginzburg-Landau equation. And what it offers you is that the ease over the microcanonical ensemble approach, where you have to integrate for a very long time for the system to thermalize. But here you can obtain finite temperature states pretty quickly, and if I remember well, you gain a factor of 1,000 or so if you want to prepare a finite temperature state. And
what's in the start?
Where?
You say the third.
Oh, this?
The number of particles.
Oh, okay. So this part I have not talked about yet. So in this formalism, you can also, introduce chemical potential to term here, and you can write an ad hoc equation for it to control the number of particles you want to put. I mean, basically, if you want to have some NP star average number of particles in the system, you can do so.
You can replace the constant gauge transformation removes it. The trivial gauge transformation removes it from the time dependent equation. The chemical potential plays no role in that case. You say it's a simple, you see e to the minus I v t over h bar, you see impose it. It's trivial transformation. So you don't need that.
No, it's T
You need to
dependent.
define the initial conditions, and that will be.
No, it's T dependent.
I mean,
That doesn't matter.
No, it's
You need to have something
no,
non-trivial.
this is
constant.
not constant in time.
It's a constant in time.
No, this is not constant in time here. This is not constant.
Even in that case, it can go. It's time dependent.
You need to violate
By gauge
unitary to
transformation.
change the particle number. So
Yeah.
where's the unitary violation?
So first, that equation is not a GPF. Look at There is
No, no, it's
I.
not. But even if it is if mu, it's time
This is
dependent
a
position.
it's a let's say GP in an imaginary time. Yeah. So that right.
How is it?
There's no I. Yes.
Yeah.
Right. Fine. So it's not. So I said it's stochastic in the Grandel equation. Sorry, should have been more explicit. So I can, add this ad hoc equation where mu is just a Lagrange multiplier, and I can write an equation for mu and control the number of particles in the system. Okay, and the temperature is controlled by putting a white noise with certain amplitude.
Okay, what's NP star?
NP star is like, let's say I want to have certain number of particles, and this imposes this.
Oh, that's what we require, and the other one what?
Yes, I'm forcing my system to have this, on an average NP star number of particles.
Can I ask questions which probably you don't care about? When you do this projection on the entire, the right-hand side of the equation, you violate gauge invariance. So, for example, if my Bose gas would be charged, and I couple it to the electromagnetic field or any other gauge field, you see, the gauge invariance will be violated. Because, for example, I can have a gauge field carrying a momentum very close to the cutoff, multiply with a wave function very close to the cutoff. I do that projection, I remove it. But then I can make a gauge transformation and I see the effect. So that's the mechanism there. So there is a problem with that. And now the question is, what about that? You see, because gauge invariance is a really fundamental property of quantum mechanics. It has to be left untouched. What if you violate is a problem. You see, I'm asking this, you see why? Because, for example, when I look at nuclear systems, we're dealing with charged particles. We have protons. Okay. If you look at the electron system, you're dealing with electrons.
Right,
you see, they're charged. No, as I understand, it's not. See, but you might have some other gauge field there, which one
yeah,
point
but
might be.
okay, it's an approximation, but I think that what is violating, it's exponentially done because of quantum mechanics. So in some sense, it's approximated because the idea of the K max, where you have a.
For the approximation, there is a parameter. I don't see the parameter.
So the idea behind this is you have a temperature, okay, kVt, and you equal that to omega h bar omega, where omega is dispersion relation, okay, and this defines your wave effect. So that should be your K max.
Can I say that the temperature should be much lower than the cutoff energy? That
much lower should be given by h bar omega equal to kVt.
Mm-hmm.
That's defining your K max by so yes, you will
but there's still the cutoff should be low. Because everything is exponential.
No, it is a system. So you have a specific heat that is linear with time, okay? That are linear with scale linearly with temperature, and not as before, like a real system in the classical limits. But it's a bit strange. But nevertheless, if you look at any thermal micro quantity in terms of intensive particles, okay, or you look at the Condorcet fractions of T over T lambda, it becomes independent of K max. So it's a bit strange to accept, but it gives a lot of prediction.
Okay.
So, I mean, depending on the situation, then I will either use the microcanonical ensemble to study thermalization of any generic initial condition, what Thomas was talking about yesterday in some sense, or and Andrew was also talking about it the first day. So I will first touch upon the turbulence in 2D Fourier truncated GPE. And just to remind, we are in a two-dimensional setting. So it admits BKT transition, for which we can define a correlations of the phase of the wave function, let's say. And what we have is below the transition, this correlation dies algebraically, and we have quasi long range order. And at the transition, the exponent is 0.25, where the condensate density, where the superfluid density jumps to 0, and is also characterized by the, and the vortices are in the form of bound pairs of vortices and anti-vortices. And above the BKT transition, you have unbound vortices, the disordered phase, and the correlation function dies exponentially. So in the microcanonical setup, we will be talking about transition energy rather than temperature. So how do I study this? I take a generic initial condition in which I put some particles in the Fourier space in my Fourier space of the wave function, which is a Gaussian distribution centered at k0 and has a small width controlled by the standard deviation. And I do this to control the amount of energy I put in the system. Okay, and I fix the total of number of particles, let's say to 1 or something. And then I play with k0 and sigma, like for example here, and I can't vary the amount of energy I'm putting so as to scan the transition and see what is happening if I'm feeding this generic initial condition. So I will just go back to my diagnostics, which I introduced, and what I observe is that if I track the evolution of the energy components, so what I see is that I have initially some incompressible kinetic energy, which very quickly goes down to 0, and it's get converted or transferred to the compressible part or to the incompressible part. No, to the quantum pressure term, which rises at cost of it. So next we are interested what is happening.
Once again, what are the two fluctuating ones?
These ones?
Yeah, that.
Okay. So
See, I shouldn't distinguish very well the colors.
Okay. So the one which is very quickly going down is the incompressible kinetic energy, and at the same time it is feeding into the
That's the
compressible.
gradient of density, right?
Yes, it's going into the density perturbation, and it's like the green part above. And the brown curve is the quantum associated with the quantum pressure energy.
And the units are
Units I have not indicated here. I mean, these are not made them. Divided by any specific unit here. So this is, we are considering a state which is well below BKT transition temperature, and now we're interested in what is happening as a function. What is happening to this energy when we look at the scale space. So I'm plotting here the compressible kinetic energy spectra as a function of k. So this curve, the purple curve, is at t equals to 0. And what I observe is that as the system evolves, the incompressible kinetic energy is getting converted into the compressible, and the spectra starts lifting up at higher wave numbers, as you can see here. And at the same time, you can see some kind of a scaling behavior beginning to emerge, but it's initially it depends on the initial condition. But after some time, you start seeing emergence of, let's say, some kind of a scaling behavior here. And if you wait long enough, this system completely thermalizes. You have equipartition of energy among all the modes. Okay.
Yes. Quick question: is this averaged over many, many runs, or these are individual
No, this
runs?
is a single realization. This is a single realization, but you can average over several things if you want to look at some specific statistical, mean or something. So you can calculate these correlation functions, which I described above, and you find exactly the same behavior. So on the left, I'm plotting this correlation function as a function of R for different energies, and what you find at energies smaller than the transition energy, they decay energy, they decay exponentially. So I'm plotting here on log, and here it is on log linear. So you can see if it's a straight line, more or less, you have an exponential decay. And you can also compute or look at the k equals to 0 mode population, the condensate population, which kind of is close to 1. Condensate fraction at very small energies, and it goes to 0 at energies above the transition energy. And at the same time, you can see that the exponent of the correlation function slowly rises and becomes 0.25 at the transition. So, but one must be careful about this, about the system when talking about such things because of Mermin-Wagner theorem, and one should look into finite size scaling and other aspects of the system. So next, what I try to do. So I am looking at the incompressible kinetic energy spectra for a slightly larger simulation sizes. So again, I feed with some energy, but this time I also play with the coefficient of the nonlinear term. Okay, and one can define a parameter which controls the dispersion by this. Okay, and I will play a movie.
G is the coupling constant.
G is the coupling constant. So for these 4 runs, I'm plotting the compensated incompressible kinetic energy spectra. So if it is to have Kolmogorov 5/3 scaling, it should come out as a plateau somewhere here, larger length scale that is smaller wave numbers. But what we should also keep in mind that we started with a situation where there was no condensate to begin with. Okay, and here we are plotting how the condensate fraction develops with time for these runs. So we can see that for the first 2 runs, it kind of goes to some asymptotic value, but we do not observe any 5/3 scaling. But for the A3, for some reason we observe some behavior which is pretty close to 5/3. So it's not very clear whether it's actually some Kolmogorov cascade in this 2D system or not. A3 and A1, that the coupling constant is different. So the amount of dispersion is different. No, it's a smaller because it's like inversely proportional to the square root of G. So, in the language we talk, is like this one will be more turbulent, tendency to be more turbulent than the other one.
What is the value of psi k max for those?
See, K max here is something like, okay. So in this setup, L is 32. So K max is and psi is I think L by square root. So it's roughly 1, I guess. Let's say for this run. So fairly large psi K max.
So it's because you have said a bit of kind of Kolmogorov when you don't still have a condensate.
Yes, but there is something happening. If you look, okay, there's another problem. I don't have exact color correspondence here. So if you look at A3 here, and A3 is B1, there is something fluctuating. I mean, large fluctuations. But on the time scale of my run, I don't have a fully thermalized system. Yes.
Can you explain again what is the initial condition in terms of the density in space?
So I put random phases, and the density I initialize it in a Fourier space with a Gaussian centered at certain wave number with some weight.
So it was small.
So it will be something like and some sigma, let's say. And this I feed it to GP and let it evolve.
So where's K naught as compared to the healing length to moment scale, and where's the healing length to moment scale then naught?
Healing length. Okay, so K psi here, let's say for the run for this run, will be like 2 pi because psi is roughly 1. Okay. And so 6. So it's like further here.
This is further, further out. So this is roughly where the bend in the blue curve is.
Yes, yes.
Where it goes deeper again. No, not that bend, but because that is a curve.
Somewhere here. Yes, sir. Okay. And yeah. And again, you have to look this in the context of 2D system where you have to take care of
Condensate you define as the K0 component.
K0 component. So now I will, yes.
So to this blue curve, so it was in this late time, it was still going up beyond the K size scale. Yeah? So K to the, if I take this times K to the minus 5/3.
Okay, you're talking about this curve?
This one, yeah.
Yes, and then?
So this is going up. So if you take it times K to the minus 5/3, it's still something like K to the minus 1 or something like that. Or is it roughly?
Okay, this one will go down, but I don't remember the scaling.
Further out, it's very steep.
Here?
I mean,
Here it falls, yeah, I mean, if there are vortices, it will be like K minus 3 or something.
Oh.
So, just because of the transform which I have.
So do you actually then sort of take out all the high energetic fluctuations through this SGPE? Because, I mean, what you're saying is you have really a steep cable minus 3 law, and then some maybe tails still there. So
Yes.
This is in 3 dimensions.
No, this is 2D.
In 2 dimensions, yeah. And then below this K to the minus 3, then it goes down a bit, which means it's something like K to the minus 1 or.
No, K to the power minus 1. I don't think so. It's K to the power minus 1.
That's about
No, but you will see at the smaller wave numbers and minus 3 at the larger wave
No, but
numbers.
then lower it goes up again. So if you multiply by K to minus 1.6, yeah, it's certainly no, below. I mean, you have everything multiplied by K to the. So this is kinetic energy. So you
It's
also have to
incompressible
divide by K
kinetic
squared.
energy.
And it's incompressible part,
Yes.
so it's no, you cannot write that so easily to another
Yeah, but
Yes.
roughly, if you don't go to the too low weight numbers, I would expect to just multiply it by K to the minus 2, and then by K to the 5/3. So this would be.
No, you have to add actually all the components. You have to do that.
Yes,
So they compress it and the compressor and the quantum. It's not so.
Okay, so I compute the number of total vortices in these 3-4 runs, and what I observed is
how do you do this?
by looking at the not so carefully. I mean, okay, I know there is a wrapping of phase. I can check that for some of them, but mostly by looking at the density depletion. And
So you look if you have holes.
yes, but also make sure that the phase wraps around it. So I didn't do it for all the runs because I mean when I was doing it a long time back, it was like very painful.
So what happens if you have the vortex on the vortex very close to each other?
Okay, so I
you cannot distinguish. You see the cores.
so possibly they are no longer hydrodynamic. I mean they're so close. So I will just and they may go into a Robert Jones soliton. They may annihilate also.
Yeah.
So you can compute the total number of vortices, which falls down very quickly, and there's some dependence on the interaction strength. And so you can define some kind of vortex number density here, and can construct a length scale out of it, and that length scale is like a square root. I mean, the wave number is like square root of this number density. So and if I compare it to the smallest wave number or the largest length scale, so it gives me a ratio which goes at the square root of the number density. So this is this is somewhere here. So and looking at the numbers here, I can see that I have a kind of a decade of range. So that 5 third which we observe could be because of what was being discussed this week, clustering of vortices or maybe, but I have not gone deeper into that issue. But I do have a range of length scales. I have a 5 third, so maybe one can put two together and.
When you generate these random initial conditions, you basically can generate this up to a certain maximum number of vortices
Yes.
in that particular box which you have.
Yes.
So what is that number? See, I don't know, you see, how you see, because I can think, see, I'll put one in the face. You see, can I do that many? A vortex per face cell,
So-
face
so-
cell.
So I cannot answer that immediately, but okay. But what I can get immediately is I have a healing length fix, so that can give me the maximum I can
Also,
fit.
that's a different, so you might occupy several cells.
Anyway, I think it's not important whatever he.
I'm sorry?
Yeah.
I think it's not important whatever he uses as initial condition, apart of the range to scale, because even if there are some vortices, as the condensate is zero, those will be ghost vortices. So
Yes,
just
they are no
one
longer
range.
they are not a hydrodynamic
So
vortices.
they won't stay that much. So those vortices are probably will be more important a bit later.
When you have some condensate building up here. So another thing is like if you have, as I for the previous one you saw, there was a complete thermalization, and I up to the maximum wave number, and here I picked up slightly higher resolution, and I showed you the evolution of the energy, incompressible energy spectra, how the number of vortices evolve. And what I do want to introduce now is that you can end up in a state when the system is thermalizing that you don't get the complete thermalization, but you have a thermalization only up to a certain length scale. Okay, and I will show you how. First of all, I pick just one run from those 3 runs and show you how the PDF of the velocity components evolve. This was studied by Carlo sometime back, and also for liquid helium experiments. And here I'm plotting the PDF of the velocity components. This is a filtered vorticity. Okay, so when you see a positive, a red dot, it's a vortex, and a negative dot is an anti-vortex. And here I'm plotting the energy spectra, all the components, and the occupation number, 1D occupation number spectra. Okay, angle averaged. So when we have these vortices, the spectra has some power law tails. Okay, and you see that the vortices quickly annihilate, move around chaotically and annihilate. At the same time, you see the energy spectra is developing some scaling, but it is abruptly, going down exponentially. Okay.
What is the cutoff date on the plot? The cutoff, the cutoff, maximum momentum.
Maximum momentum will be given.
No, on the right hand side, it's where that disappeared. It's 100 or it's 100.
Okay, I don't understand completely, but the full
No,
spectrum.
you have a maximum momentum cutoff.
Yeah, K max.
And then K max.
So
Where is it on that plot?
On that plot, you see on the horizontal
Oh,
axis.
okay, okay.
On the horizontal axis, where it's K max, what's the value?
Oh, I don't remember the number, so it's 500.
One something divided by 3, no? 300.
No. Actually,
So it's further
different. No. The thing is, here I have a L which is 32. So it has to be 512 multiplied by, let's say, 6 divided by 32. So that's my K max.
I cannot see it for you.
That's
So 5 is roughly 5, so it's roughly 100, roughly here.
It's 96.
Yeah, roughly 100.
Oh.
Yeah, can I ask, so why is it actually falling down to 0 before that scale?
That's the story I was going to tell about. So it's a system is like kind of self-truncating here. I mean, you have a partial thermalization below certain wave number, okay, and the scalings here are, I mean, well defined, and we want to study how this front moves further, okay, and this we will see depends on initial condition, on the amount of dispersion you have in the system, and so on and so forth.
But it's
Yes. No, no.
so you're saying this is still moving to the right.
Yes, I will show you. So, in fact, if I play the movie again, it slowly moves, okay, to the right. So the system has a tendency to, thermalize more and more, and we want to study like whether it really thermalizes completely or never thermalizes, or if it thermalizes at what rate this wavefront moves. Okay. And at the same time, you can track the energy components, which I've shown only for the short time, but in the longer these energy components saturate.
So just to understand, so at the end, what you have no vortice anymore.
No, in this system, no. I mean, for one of the runs, I don't have, I'm left with no vortices.
So where is all the energy sound?
It is in the sound mode and also in the quantum pressure term. It has gone into that.
Shouldn't you then see it in this distribution?
Apparently everything is here.
Yeah, but k to the minus 1, this is n. N is k to the minus 1, no?
Yes.
So that's kind of the signature of having a few vortices left. No?
That one, no. Is that one?
No, this is actually n. N is
N?
again. Yeah, so that's the number, but why is it k to the minus 1?
So my nk is an average over the sum. Okay. Average over the radius angle. So it's a 1D spectrum.
What is decay there? Decay? What is decay?
It's replaced by the sum, I think.
Okay, no integral, but integrated over all k's.
Yes.
Then square.
On a circle.
Square is moving slower.
Yes, sorry.
And then essentially angle average.
Angle averaged. No, sorry. Not average, sum. Sum over the angles.
Yes. Okay, over all lattice points, no?
Yes.
Yeah, that's fine.
On that circle.
Yeah, but why do you get k to the minus 1 then and not k to the minus 2?
No, multiply this by omega, by k squared.
You get
K to the 1,
yes, you get k.
What is
It's because of the decrypting, right? It's doing that's summing, not everything.
Yes.
You get effective k from the radial decrypting.
So if you sum that n of k from k equal to 0 to infinite, you get the total number.
Total amount of
If you take the average rather than taking the sum, you get 1 on k squared.
So your angle average brings in another factor of k. That's what you do. You have this factor of k from the angle average in there.
Yes. So I think slightly different the way you do it.
Well, it's just
yes. So I had a partial thermalization up to such a wave number which I call Kc, and then I compute this Kc and want to study how this system is thermalizing by looking at the evolution of this wave number as a function of time. Okay, whether it's self-similar or rather how it grows. So I prepared here several initial conditions for several values of the interaction sent, but let's focus only on this one. And what I have here, G is fixed. I give them, and all of them have the same energy, and the number of, and I increase the size of the simulation. Okay. So
is it coupling constant G?
G is the coupling constant.
Is that weak?
Yes. We are in a weak.
It's weak.
Okay, you have to think in terms of some units which I'm not.
Yeah, but that's what I'm asking. Is that weak coupling force?
Yes, for the
Because
system we are
these numbers, you see, right?
Yeah, so
Numbers, you see, not in arbitrary units.
yes. Okay.
So do you simulate a weakly coupling forcing gas?
Yes. So
all the time?
yes, all the time it's weak,
Okay.
or rather, we are only concerned with what's called weak wave turbulence.
Well, that's another classification.
Yes, but
it's weakly coupled forcing gas.
weakly coupled Bose gas all the time. So what we observe is like the 64Q loses its spectral truncation and completely thermalizes, and then you can see the tail for the 128 square was lifting up. It will go if I run longer thermalize, and similarly the others also rise. Okay, and it moves from here to here, the wave front. Okay, and now I mean till now what I was doing a microcanonical simulation of the GPE, but takes a very long time to thermalize and to monitor such effects. So what I switched to the stochastic Ginsburg-Landau formalism, which I had introduced. So what I essentially do in that, I generate spectrum which are partially thermalized, let's say up to certain wave number. Here is the K max of my simulation, and I call KC initial. So I make it thermalize here till some wave number by hand, okay, in my system, and let it evolve. And want to see as a function of let's say the amount of dispersion which is there initially in the system controlled by psi KC in, which I'm let's say on these plots on the lower panel varying from 9 to 15 to 20, or rather 6 here. Okay, and quite small compared to this. So if you look at the kinetic energy spectra, so for this case, this was the initial spectrum, and the thermalization slowly extends, the tail lifts and thermalization extends to higher wave numbers and will eventually thermalize. Okay, and if you look at this one, it is also starts lifting but growing slowly. Okay, and for these one, it just kind of smoothens around the KC initial, and I will compute how this KC behaves as a function of time. Okay, so what I find is that I have plotted, let's say, KC going as t to the power alpha. Okay, so it for most of the runs it's like 0.25. Okay, there is some kind of a self-similar growth, but then there are some situations in which this exponent becomes very small. So the growth is kind of logarithmic. So the system may remain self-truncated. That's what we are observing here. And something similar was observed by Giorgio and Mark in 3D systems. So to conclude this part, so we identify kind of 4 stages in the dynamical evolution of the dissipation-less unforced Fourier truncated GP equation in 2 dimensions. And there are regions of initial transients and which very much depend on the initial conditions. We then begin to observe some onset of thermalization, that is some scaling behavior, and spectra change with time and depend again on the initial conditions. But when we enter the region of partial thermalization, there are some universal scaling behaviors which are independent of the initial conditions. Okay, or we can have a self-truncation at wave number KC in energy spectra, whose dependence on time can be either t to the power alpha, self-similar, or they can be growing logarithmically. Or else we can have a completely thermalized phase with universal power laws in spectra and correlation functions, and they have to be consistent with the BKT phase. And in fact, even if you look at the occupation number spectra, you have to take into account the exponent which is in the correlation function. You can relate it with the occupation number spectra, So instead of observing k minus 1, you should observe k minus 1 plus eta, something like that.
Can we go back to this slide? So here you don't do dynamic, right? You do stochastic.
Yes. I prepare my initial data using
How you
stochastic.
prepare, I don't care.
No.
But you do stochastic.
No, I prepare my initial data only using stochastic. Then I take that and feed it to GPU.
Oh, my God.
So that's for the initial state. And that was one of the reasons they developed this stochastic method, so as to quickly have some thermalized state, so as to bypass the long time evolution which you observe in a microcanonical.
But why do you have the sharp cutoff?
Because I'm imposing it by hand. Because
in the stochastic equation.
In the stochastic equation.
It's
I mean, it's
artificial, right?
Yeah, it's artificial in the sense like you have k max, and here you are setting kc in by hand and putting the modes.
So it's just like if you just take the initial state, you just cut it off,
Cut
filter
it off.
You're telling me that you understand what they did mathematically. So
Yeah,
you want
yeah.
to understand the physics.
No,
So then they don't care. You see the math. They want to understand the physics. Why do you do that? See, because if you thermalize, you see, you cannot have an arbitrary KC there. You see, thermalize, you see in the entire space. You see, then I'll understand.
No,
So you construct a very artificial initial
but
state.
this is just first to mimic what we were observing in the microcanonical evolution, that there is a system spontaneously develops some kind of a self-truncation in the wave number space, and your spectrum doesn't move beyond that. And
So can I translate this into another language?
Mhm.
The GP, dynamical GP truncated, is very truncated. It's not an ergodic system. Can I say that?
No.
No?
No.
But if it's ergodic, you should thermalize. And it doesn't.
And it does, but there are very different times.
Yes, that's what.
You see, this spectrum, none of them is fully thermal.
No, but it depends
See,
how long you
look
have
at
to.
the high momentum, they are not thermal.
Yeah, but that's what he showed later.
This is what we're interested in, like how they are thermalizing. So we are letting it evolve and want to see how it thermalizes.
You can imagine the system, you have two time scales. So first, you have vortices, they interact, they manipulate, they do whatever they have to do. Okay,
So
and this
can you tell from this simulation that that's the case? I mean, that you have two times scaling
That's
was the
what we
origin?
that's what we showed before, that you observe this k squared up to a given k that is much smaller than the k max of the simulation.
The K-max simulation is 100, I think we established that.
Yeah.
Right? Yeah.
maybe not much, but smaller.
Like your 10 is the plan.
Well, it's like the same.
Okay.
Okay, go ahead.
Okay, so you can use this SGLE formalism to study finite temperature effects. Yeah, I will just quickly show. And which Georgia and Mark had used in 3D to study some dynamical effects like contraction of the vortex ring because of mutual friction. So you can play the same game and do that here in 2D. You can prepare a vortex pair given by this wave function and multiply it with a wave function which represents a thermalized state, multiply them together and feed into the GPE and let the system evolve. And what you will observe is that because of the mutual friction, the vortex pair contracts. And if you plot the size of the pair versus time, you can see this is a plotted V square here. It's a vortex pair. So I have plotted a density field, and these blue dots are representing the vortex pair. So basically, I mean, the vortices move like this in the superfluid, and at the finite temperatures, you have to account for the mutual friction term, and you can do a little calculation and show how the pair moves, and compute these coefficients. And we computed the one which is responsible for the contraction, and you can get it as a function of temperature, which I am writing here, and it slowly increases with temperature. I have done it only for low temperature states. Okay, so probably will not go beyond, but what I wanted to motivate and discuss is that to go to the continuum limit and talk about, let's say, to begin with 2D systems, and can we use HVVK formalism, given that this week and also that people have been talking about clustering of vortices, can we dare to go beyond and say that you have a larger clusters, and can we coarse grain, and so that we can develop some kind of a two-fluid model? If yes, and can we do some HVVK simulation and see what is happening in that system? So we did it some time back in a 2D box and tried to study the behavior of cascades. And the system is very much similar to the classical fluid, which you expect because you're bound to be above certain above the vortex intervortex length scale, which I had defined earlier. And I'm also assuming that I have like formation of these big clusters which you can take to the continuum limit, but the things are hazy, but we decided to go ahead and do. And then you can also examine the finite temperature effects, like the mutual friction, how it couples the two fluid. Essentially, you borrow all the things which have been done for the 3D HVVK equation. So what I'm doing here, I'm plotting the vorticity field, okay, on the left for the normal fluid, on the right for the superfluid, okay. And first what I'm doing, and their viscosities are different. Let's say in my numerics by a factor 10, okay. And I produce no coupling, zero coupling. And in the other case, I put some coupling by hand, okay, because I don't know what is the value of B for this system. Okay, so I have played with several numbers and I find the picture being consistent.
Maybe one is too small, maybe it's too large.
I said, I mean, I'm just playing with the numbers here. I'm not, I don't know, but because there is no data.
Scale. See, that's the reason I'm asking. Probably from the scale you can judge.
If it in B is the for one and friction,
It's the whole.
if you go around B equal 1, you're already in the lambda phase transition region. So it's very
So B1 is large?
yeah, very
Largest.
very large.
Okay.
But it is dimensional, so it doesn't.
Yes. So for the first system, when there is no coupling between the two fluids, the one with a smaller viscosity, of course, goes to a turbulent state, and the other one, for some reason, goes to a frozen state. And now, if you introduce this coupling, this transfers. There can be now a transfer of energy from one to the other, and this also drives the other to a turbulent state. So now you can have turbulence in both the components. And introduction of this coupling also then modifies the energy spectrum, how it behaves. So you can see the energy spectrum is very similar at small wave numbers now. And
So it's decaying. It's decaying.
no, it's a force simulation. I mean, you take a standard 2D Navier-Stokes simulation, and yes, you do get an entropy cascade. Like
the forcing is a low K.
Forcing is a low K here. I mean, I just wanted to qualitatively show the pictures. So then what you can do, if you believe that this can be applied to, to the scenario where you have this clustering of vortices that you can go to a limit, you can force them at some small length scales, and you can look at what is the nature of the cascade. You do get a classical like picture that you get an inverse cascade of energy, forward cascade of entropy, and you can look at the fluxes that the energy flux is negative and entropy flux is positive on on the other side of the positive number. And you can also characterize how the mutual friction is transferring energy across the scales. So getting transfer from the dominant component to the other. Let's say you're at a temperature, low temperature, and I'm forcing the superfluid. Then the superfluid is transferring energy to the normal component. You can monitor this through the.
What are the different curves in the motion friction transfer?
These different curves correspond to these different temperatures, and solid lines will be corresponding to the normal fluid, and the dashed line to the superfluid. And then I'm also forcing only the dominant component. Only one component is forced. So let's say below 0.5, my superfluid is the dominant component. I'm forcing only that. So here you can see, I mean, the energy being transferred from one to the other. And but also at the at the large length scale, you also see the effect of friction. Okay, I've introduced that also because to respect the numerics, and at the same time there is an inverse cascade, so I need to remove that energy from the system. So it is also affected by that. Then you can also study locking, and you can also study locking and characterize several PDFs, like how is the angle between the two. So you see it's like maximum alignment along when they are like the theta is 0. You can also get some estimate of these ratios. I mean, we also have some little prediction and theory about it, and it's kind of universal, independent of the friction and other things we put in. And the same thing, I mean, this was studied using Biot-Savart coupled to a normal Navier-Stokes equation and observing one-to-one correspondence in some sense. Like here they have got the isosurfaces of vortices, and then here you have vortex filaments. And so the similar thing also happens for 3D HVVK equation. You get a locking, and you have a direct you have a cascade of energy as well. I'm not going into that. You can also characterize higher order increments of velocity. Look at intermittency. Recently people have been looking at that, and it's quite an active area, but not touched that. And okay, I will have no time, so probably Mark will talk about this. So I just want to flash a picture of our recent simulation, which is kind of state of the art. And what I'm showing here is a t equals to 0 simulation of a Gross-Kaczynski equation at 4096Q. And I'm going to show you the isosurfaces of vortices here, okay, in a turbulent state. And it's a decaying turbulence. There's no forcing, no dissipation. I start with some flow, which is a Taylor-Green flow, okay, and let it evolve. And at the instant of maximum dissipation, what I observe is shown here for the vortex isosurface, for the I'm showing density isosurfaces basically here. So these are.
You said there was no.
So the dissipation is, I mean, the thing is going into the sound modes and the other energy components. It is in that sense. So you can try to track, how these things evolve in time. Well, Mark will talk about it next week.
That's GPE simulation.
That's a GPE simulation. No forcing, no dissipation. You just start with some initial configuration and let it evolve.
Okay, did it go?
Okay,
did it go?
No, the simple truncated, fully truncated GPE. And so what you observe, there are some structures where you have high density of vortices, and also some regions where it's like you don't have these vortices. I mean, they're low, vortex density is low. And what you also observe, if you zoom in, a whole lot of other things, like you can have very complex structures, some linked structures as well, rings, and you can also see some waves on these vortices, which are FPS.
If you look, those are simply lines, so there is no information about the direction.
Yes.
But are they locally parallel, or are they bundles? Are those bundles?
To some extent, they're not completely aligned, but to some extent there's some alignment. And this is why I was asking, like, is it the time now to take these simulation and start talking about two-fluid picture from the GPE? And like I talked about the 2D system, but here in 3D. But I think, you know it much better, since we don't have a large polarization of the vortices. If we do a coarse grading, we don't get a true estimate of the vorticity. And you can look at the energy spectrum, and with this big simulation, you can resolve now the direct cascade of the Kolmogorov region, and also some kind of and the Kelvin wave cascade also.
In physical units, what is this time? So how can I relate it to some time? Because it's arbitrary, and like something which I can actually know in real nature. So I don't know what the T0, T4, T8.
Okay, I mean, you can always, I mean, here I can always write it in terms of my, take C and psi.
I don't know, you say, is this a big time? Is it a short time? You say,
okay, in terms
by what measure?
If you take these, C is the speed of sound here,
Yeah,
and
that's
psi
length.
is the hearing length. So in terms of this time, which is a very small time, no.
Divide side by C.
So if you do this,
Psi by C.
yeah.
Okay, that's a time, but that's how big is this?
So this is a small.
What is this?
If you compare to this, then the times I'm showing here is very large when compared to this.
10 times, 1,000 times, I don't know.
Thousands, several thousands.
Looking for an interpretation. So the time scale is given by the sound speed and the hearing length. The hearing length essentially is the size.
Yeah, but in this unit, what is that? You see, that's what I don't see the units.
If the time units are large in those homogeneous visualization, essentially means that you're waiting very long times compared to the time it takes for the information of a vortex moving and radiating sound disturbing another vortex. So it's really long.
Well, you see, I have two time scales. See, that would be one, and the other one it will be the size of the system of a C. There will be another unit.
Rather that.
Huh?
Rather than big.
So this is smaller than the sound propagating across the system, or it's much larger?
Much smaller.
They are comparable.
Much larger.
Okay.
Time.
This is
Okay, that makes more
Time.
sense.
Typically in turbulence, you look at
Time is
you normalize everything in terms of the largest time,
Okay.
the time of the big area
Okay.
of the system.
That
Could be more than one.
Actually, this was also, I mean, we completely understand this confusion arises, and we are aware of this if we may put it this way, but this was done to compare it to the classical Navier-Stokes simulation. Okay, I will not say anything more about it because you will hear about it next week.
What's the healing length scale here?
The healing length scale, I think.
The picture is around 2,000.
Yeah.
Compared to this.
Say it again.
1,000.
Yeah.
A bit less.
And
I mean, we cannot afford to, super resolve like the 2D simulations which I was showing you earlier. Some of them were like ridiculously resolving the healing length. Like I was giving.
I mean, your policies are of the size of the healing length. I mean, how can you trust these simulations if you don't have
No. There
a
are
lot of magnitude, right?
no. There are several points I push it for. It's usually in particular this simulation is much better, but people say. So you put so the vortices are very stable. Topologically, it's usually enough to put one or two measurements. In here, plus 4 points.
Can I ask again also maybe the simulations which you showed before with this stopping of your thermalization? Yeah. The initial state you said is a Gaussian distribution around some point, so it's sort of falling off exponentially. And you take random phases. Yeah, and then afterwards you just run the GPE.
I just run the GPE.
Yeah. So what it means is that your high occupation numbers are actually initially sort of essentially zero. Okay? And you might have some random phase in there, but there's nothing in there. That's what you run.
Yes.
But I would actually have sort of very strongly the feeling that then you are not describing a quantum fluid because you have empty modes out there. And it's well known that when you run the GPE with empty modes, it will just not thermalize because you're essentially neglecting any quantum fluctuations. And so what you're describing actually is a classical system. You describe a classical fluid, which is kind of just the same as the quantum fluid, but it's not sure. It's nothing to do with the quantum fluid when you go into
But you
efficiency
know, they compensate by
where your occupations are falling below 1/2.
No, but
You need at least 1/2 particle out there in order to be have valid.
the time scales on which we observe this, partial thermalization and other things.
Yeah.
I mean, we already have, some occupation number developed.
No, down there I'm fully happy, yeah? But when you're saying it stops stabilizing, then this is
No,
simply because
okay.
you're saying sort of it stops moving out to the edge of your lattice halfway down. This is because you're just not describing a quantum fluid down there anymore, because you're failing all the quantum.
No, but there are two things. So one is what I put at t equals to 0. That's a different thing. And when I'm describing the partially thermalized state or talking about the truncation, there I have something which is, going down exponentially. There is something.
That's a transit state, but in the end, you should always have rather quick kind of thermalization to a k to the -1 or 2 scale. You had a k to the -1 right to the edge of your lattice. Otherwise, you're neglecting the quantum ground state fluctuation, and that's not a quantum fluid anymore. So this is the well-known problem of the semi-classical simulations of the the quantum fluid, that it always thermalizes to the lattice cutoff. And if you shift out the lattice cutoff, it just thermalizes further. And if you don't take into account these fluctuations in your initial state, then of course it stop and be very slow in filling these modes. But that's not a quantum improvement. It's a classical nonlinear.
Therefore, will slightly speed up the process of this KC moving to the right. But nevertheless, the time scale of the thermalization until this kind of subfluctuation number is much faster than this KC move. It's true, if you populate with a 1/2 of particle energy, it will be a bit faster, but nevertheless much lower than the dynamical time scale.
Well, at least you shouldn't have the logarithmic close in the end. I mean, it should be at least so. In a quantum system, when you start with empty modes everywhere, and you have a local scattering, which it is, it's a local scattering in space, then you will have kind of scattering in all modes at equal kind of probabilities, and you would just sort of in the classical approximation, you would fill up all these modes essentially exponentially fast. And then, of course, I should kind of, many-body system thermalize the points to the Rayleigh Jean state. But you will not get any kind of exponential cutoff from your semi-classical simulation. At least this is I thought is the status of what. I mean, we know that when we sort of underpopulate our modes there in the truncated figure, then we can also stop kind of filling them up. It gets much lower, but that I would think would violate this approximating quantum system. Would be careful at least. I mean, of course, you have then again other problems. If you, for example, put the cutoff too far out, then you get thermalization where it shouldn't be, namely to occupation numbers below 1, below 1/2. This is again, of course, not a quantum system.
Has anyone looked at these?
Well, there is quantum fermions are like that. No, don't say that.
Yes, but you shouldn't expect it from the truncated figure to see it.
Has anyone looked at these types of thermalizations in a multi-channel model? People know. I mean, they're much more expensive.
Why do you ask that question?
Well, because then you'll have more quantum fluctuations.
Not necessarily.
Okay.
Yes, there's another question.
Oh, sorry.
Sorry, can you question about something done before?
Okay.
Can you go back to the picture of Copeland and Morris?
The answer is yes.
To the picture now?
Yeah, that picture.
Yes.
So it's about locking.
Yes.
So that was in 2008. So they used the frozen DNS.
Yes.
Many years before that, I tried it with an ABC flow, which is much simpler. But rather than keep it frozen, I had a time-dependent ABC flow, which was essentially doing this. And I found that actually there was locking, but actually, if you move the normal fluid vortex tubes, the ABC flow fast enough. And the superfluid vortex line could not, in 3D, could not actually follow.
Adjust to the.
They were left behind. So the locking seemed, to me, at least with a very simple ABC flow model, somehow frequency dependent. So, do you know more about this?
Okay, so I've not looked at the vortex filament or the normal the Navier-Stokes coupling this way, but I've only looked at the two fluid where I'm taking superfluid also as a field and normal fluid also as a field. So there
does the locking depend on the fields?
So all I can say, I mean, they are able to mimic at least at the large scales. You see, I mean, I have a turbulent flow here of the let's say I'm forcing the normal superfluid here, and the normal fluid is able to follow it. But what problem I can see is that the parameter B which I'm putting, how realistic it is, and like maybe you have put in 3D system, so that can also play the lag with which it follow the two fluids follow each other too.
So it's strongly coupled.
It's strongly coupled. Yes, because I don't know what to put for
the temperature. Or one should be in the Lambda region, so 2.17. Very close to also.
But Carlo, can we take what you're saying to the 2D setup as well, because this is a 2D setup also. So these coefficients are more or less dimension independent, you would say.
So the calculation power made originally is 2D setting. It's calculating for a straight vortex.
But I don't know. One should look at that carefully because
2D is very good system.
Yeah, should be done. Because clearly, if the locking is perfect, that essentially try to cancel the friction. But
yes, so you
at the high frequency, the locking phase in some sense provides dissipation.
Yeah, so I mean, okay. If you look at the spectrum, of course, it is well known. At higher wave numbers, there is a kind of a decoupling. This is a 3D simulation, and I'm showing you the energy spectrum of the superfluid and normal fluid at different temperatures, but with more parameters taken from the spectrum. You want to say something?
But you have something like you are looking at the cosinus of the velocity.
Yes, I was looking at the cosinus of velocity for 2D, but here I'm looking at the angle theta. So, okay.
This is a
I have plotted the PDF here, so I mean, there is actually, if you look at the cosine of the theta, you see, basically around theta equals to 0, the PDF is.
which scale the couple?
The largest scale. Or
no, they are coupled at large scales, but they decouple at
small scale. They decouple at the small scale.
And how small? Larger than the Kolmogorov length.
Of course, yes. I mean, that's the smallest length scale here.
And what controls the ratio between that scale and the Kolmogorov?
Easy. So essentially, these frequency-dependent locking will explain.
Yes, I mean, like if you increase B, like in 2D case, I could unphysically keep increasing B, and then what you see is that the spectrum starts becoming closer and closer. The locking actually extends to smaller length scale as well, but that's maybe unphysical, and also it will start. I mean, mutual friction itself will start becoming weaker, I guess.
And another question.
Yes.
In the very last slide, there was a picture with the K-5 third spectrum. So I bet that is the bottleneck problem.
Yes.
So in between the Kolmogorov spectrum and the Kelvin wave spectrum, there is this region which is a bit troublesome. Now, when the idea of the bottleneck was introduced, the expectation was that there would be something big there. But this seems to be perhaps the best evidence for the bottleneck available, because there are no experiments which show any bottleneck. So this is the best.
There are no experiments that can look at smaller scale.
Yes. Well, what in a real space, what do you expect to see there in that region of where you go from one spectrum to the other?
Is this the region in the middle?
Yeah, the region in the middle, where the energy comes from the three-dimensional Kolmogorov cascade. Would like to go down helical Kelvin waves in one dimension on each vortex line, but there is some impedance in a sense, and so it builds up a bit that region. So the expectation were initially when the idea was proposed that it would be a large impedance. It seems to be like that. Is there a way to pump it up or make it more dramatic by tweaking your model? To suggest some
Tweaking a model, I don't think so. By tweaking a model, you can do so.
Yeah, so it's a kind of it's GP is conservative, but we can call that a decaying, because then it's found from the vortex out, from the vortex to the sun. So I think it's if you, at least for your thoughts, you are able to force at that scale to put some, to imprint some vortex in that scale, that will increase the flux. So what is the idea for the modeling? That you have a transfer that is given like Kolmogorov. Okay, so it's a very strong linear process. On the other hand, the right, you have Kelvin waves, the weak cascade. Okay, so if you can start putting more and more and more vortices on that scale, you increase the flux at the left. Why don't you not touch the one at the right? So from there, you could expect to come. The problem in practice is that you cannot really force the GP. Because if you start forcing, you lose a lot of sound, and this mess up all this Kolmogorov. So maybe looking at participated GP in a very kind of.
If you get a non-local or modified GP with a kind of higher powers representing rotates, you can't actually building up either the non-local GP or
so the non-local, I don't know where you should put them in the auto minimum.
then what are you planning?
I guess this discussion will continue in the evening. This seems like an interesting
Yeah, we probably
point.
should wrap up now.
Yes.
We'll go, and then let's come back and resolve some of these issues after your session. Okay?
Okay, thank you, speakers.